Now that you've been introduced to parent functions, we're going to shift them on the coordinate plane. When we move all points in the same distance and the same direction, this is called a translation. So let's graph a pair of functions to illustrate this. Y equals x squared is the parent function that you graphed in the introductory lesson. So I'll make a table of values for y equals x squared. And when we square numbers, it's important that we see a couple of negatives and a couple of positives. So I'll use -2, -1 for our negative numbers, 0 for in the middle, and 1 and 2 for the positive numbers. Let's square those numbers, multiply them by themselves, and that will give us our y values. Now let's plot those. And typically for a parent function, we'll try to plot 5 points if we can. We can actually plot a couple other points because 3 squared is 9, so the y value for x equals 3 and x equals -3 is +9. Now, using a different color, let's illustrate how we can graph y equals x squared plus 2 using a table of values. So, when I replace x with a number, I'm going to first square that number and then add 2 to that result. So an extended table of values could be the one that we have right here. I'm going to use those same couple negatives and 0 and a couple positives, square those results, or square those x values, and then add 2 to each, and that will give us our final y values. So the point -2, 6, -1, 3, 0, 2, 1, 3, and 2, 6. When we connect those points to form the function, we can observe that this is translated up to, or shifted up to. All right, now let's take a look at an absolute value parent function. When we use an absolute value parent function, it is important that we replace the number inside the absolute value with some negatives and some positives. So I'll use those same values that we used for y equals x squared, and then take their absolute values to find the y value. So -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. And what we can observe from this is that we have not a curve this time, but 2 rays that emanate from the same vertex, or 2 half lines if you want to think of it that way. And this forms a nice V shape. That'll be characteristic of our absolute value functions. If I want to create an extended table of values for the other equation, then I can use the x values as input. In order of operations, we must take the absolute value first and then subtract 3 from that result to get the y value. I'll use the same inputs and take their absolute values and then subtract 3 to get the final y values. Now we have -2, -1, -1, -2, 0, -3, 1, -2, and 2, -1, and this will also form a V shape. And this graph is just the original parent function graph translated down 3. It's your turn. Pause the video while you're doing this one. For this one, it may be helpful to graph the parent function first, and if you do so, that's fine, but you can also create a table of values for y equals the square root of x plus 5. The first operation is taking the square root, and then the second operation is adding 5 to that. When we take a square root, we have to use friendly values, that is, the values that we can easily take the square root of and get a whole number, 0, 1, 4, and 9. So keep those values in mind when you're plotting this kind of a function. And the square root function will have that characteristic hook look to it, and this is a translation up 5 of the original parent function. Okay, let's take a look in example 3 at the graphs of y equals x squared in blue and y equals x plus 3 squared in red. What effect does adding 3 here seem to have? And that is that it translates the graph 3 to the left. Now, when we added 3 before, it would translate the graph up 3. But this addition is happening on the inside of the squaring, so it's going to affect the input value or the x value. Let's use this result to predict what the graph of y equals x minus 2 will look like. If you remember what the graph of y equals the absolute value of x looks like, a quick table of values will uncover that. If you don't remember, we can always go back to the table of values and take their absolute values of the x's, a couple negatives and a couple positives, 0 in between, and that will give you the shape of that parent function. And if that's the parent function, then we can take a look at the transformed function, y equals the absolute value of x minus 2. My order of operations is slightly different now that the x minus 2 is inside the absolute value. When we replace x with a number, we have to subtract 2 first and then take the absolute value. When we take an absolute value, we want to consider a couple of negatives, 0, and a couple of positive numbers to take the absolute value of. Since we're taking the absolute value of x minus 2, then x minus 2 needs to have a couple of negative values and a couple of positive values. So the absolute values, or the y values, are 2, 1, 0, 1, and 2. And then to get back from the x minus 2 values to the x values, we're going to add 2. So if x is equal to 0, the y value is 2. If x is 1, the y value is 1. Oops, and I need to graph that correctly. And then if x is 2, the y value is 0. So 2, 0, 3, 1, and 4, 2. And you'll notice that characteristic V shape is translated 2 to the right. That may seem a little bit counterintuitive, but when we're working with inputs, the direction effect is opposite of what you might expect, because we have to undo the operation of minus 2 in order to find our x values. Your turn. Try the following. Try A first. Graph that without using a table of values if you can. All right, here in blue is the graph of y equals x minus 4 cubed. It's just a translation right 4 of the graph of y equals x cubed, which is one of our parent functions. Now try B on your own and pause the video while you do this. Here is the graph of y equals the square root of x plus 5. It's just a translation left 5 of the graph of y equals the square root of x, which is the parent function shown in red. All right, now in example 5, we're going to label each with the correct equation. So you'll notice that both of these are translations of the cubic function y equals x cubed. So for the green graph, that's a translation right 3. And so right 3 would be y equals x minus 3 cubed. You'll notice that the minus 3 is on the inside of the cubing, which means that it's going to affect the input value or the x value. So we're translating to the right. And our purple graph should be y equals x cubed minus 3 because that's a translation down 3. In B, we have translations of the square root function. The blue graph is translated up 2, and you'll notice in the first equation that we have the plus 2 outside the square root. That's going to be an effect on the output variable, which is y. And then for the pink graph, that's got to be y is equal to the absolute value of x plus 2, because the plus 2 is on the inside of the square root, which means it's going to affect the input variable, which is the x variable, so we're translating left 2. And lastly, in C, we've got a green graph, or something that looks kind of green. That's a translation to the right 4 of the squaring function, so that must be y is equal to x minus 4 squared, where the change is on the input. And then the red graph is y equals x squared minus 4, because the minus 4 is on the outside of the squaring, which means that the graph is translated downward. We can generalize all of these translations for any parent function. The graph of y equals f of x plus d, where the d is added to the outside of the function, translate the graph up if d is positive, and down if d is negative. The graph of y equals f of x minus c, the x minus c is on the inside of the function, and that's going to translate that to the right if c is positive, and to the left if c is negative. When there are two translations, it can be helpful to note a new origin. That's the point where 0, 0 is translated, and then use the pattern of the parent function to graph from that point. So, for this parent function, we have an x minus 3, so that means that the graph is translated 3 to the right, and then squared, minus 5 is on the outside of the squaring, so the graph is translated down 5, and so that means that's where our new origin is. I put that in the wrong space. That is the new origin, 3, negative 5. I'm going to note that point, and then graph points from that new origin. So the squaring function, 0 squared is 0, so that's 0 up from the new origin. And then when I move 1 to the right of the new origin, I'm going to go up 1 squared, which is 1. When I move 2 to the right of the new origin, then I will go up from the new origin 2 squared, or 4 units. And then to the left is negative. So if I move to the left of the new origin 1 unit, then I'll move up negative 1 squared, which is positive 1. If I move left 2 units, I'll move up negative 2 squared, which is 4, and our parent function translated right 3 and down 4 looks like the following. All right, let's try in B an absolute value function. If we have an x plus 2 on the inside of the absolute value, that means the new origin's x value is negative 2. If we have a plus 5 on the outside, that means that the new origin's y value is positive 5. One other way that you can think about this is if x is equal to negative 2, then y is equal to the absolute value of negative 2 plus 5, which is the absolute value of 0 plus 5, which is 0 plus 5, or 5. Our parent function is y equals the absolute value of x, so I'm going to mark the new origin, negative 2, 5, and then graph the parent function from there. We have 1 point that's on the new origin, move to the right 1, and we move up the absolute value of 1, which is 1. move to the right of the new origin 2, and we move up the absolute value of 2, which is 2. When we go left, we're using negative numbers. So left of the new origin is left 1. The absolute value of negative 1 is positive 1. Left 2, absolute value of negative 2 is positive 2. So there's our V-shaped graph, which has its vertex at the new origin. For C, we're going to use a parent function of y equals the square root of x. And our new origin point is negative 3, negative 4. I'll mark that point off. And then mark the point 0, 0 from the new origin. And then when we go right 1, we go up the square root of 1, which is 1. When we go right from the new origin 4 units, we'll go up the square root of 4, which is 2. When we go right 9 from the new origin, we'll go up the square root of 9, which is 3. And that gives us our translation of that parent function. Lastly, we're going to consider the parent function y equals x cubed. If we have an x minus 1 on the inside of the function, or the inside of the cubing, that'll give us a x coordinate for the new origin of 1 and a y coordinate of 5 from the plus 5 on the outside. So I'll mark off our new origin, which is the point 1, 5. And from that new origin, if we go right 2, we're going to go up 8. That point's not going to quite fit on the graph. If we go right 1 from the new origin, we'll go up 1. If we go 0 right of the new origin, we go up 0. 1 to the left, we go down 1 cubed. In other words, negative 1 cubed is negative 1, so we go down 1 rather than up 1. We go 2 to the left of the new origin, we're going to go down by 8, which is 2 cubed. So that'll bring us to this point, and now we can connect for a nice smooth graph. And that's it for the notes.